Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, in previous section 7.2, we introduced three different page replacement algorithms. We talked about optimal and FIFO, and also we talked about the LRU, the least recently used algorithm. Now, optimal is the best. However, it's not realistic, right? It requires the knowledge of future page references. Now, FIFO is simple, but FIFO has its own problem. And in the next slide, we're going to even talk about a very big problem for FIFO. So making FIFO not really practical algorithm without any modification. So LRU, select the page based on the page reference history. So this is doable. However, the LRU requires the queue of pages, and it requires the modification of this queue at each memory references. So this actually makes the algorithm too inefficient in practice. So, which means that the LRU should be somehow modified as well. You cannot use the LRU as it is. So in this section, we can actually talk about the approximations of the LRU algorithm. Okay, so one of the simplest page replacement algorithm is FIFO. So FIFO is simple, and it's also cheap and intuitive. However, FIFO performs poorly in practical applications. Now here's a big problem for FIFO. Now this algorithm experiences belated anomaly. Now what is belated anomaly? It's the phenomenon in which when you increase the number of page frames, it will result in an increase in number of page faults, for certain memory access patterns, including the FIFO. Okay. So FIFO is really used in its unmodified form. Okay. Now what does belated anomaly means to us? So with our common sense that if you actually use the page replacement algorithm, and if it's performed poorly, that's because the memory size, the physical memory is probably too small for the number of pages. So most of the time the memory is full, so you need to do the page replacement, right? Now with our common sense, if you increase the memory size, saying right now it's 2 gigabytes, but now I increase to 4 gigabytes. So you think that this is going to basically decrease the number of page faults, right? So that way you're going to increase the performance. Now belated anomaly says for FIFO, this may not be the case. This is really bad, right? So that's the problem why FIFO is not realistic. Now for LRU, as we mentioned, it has another problem because LRU requires the queue of pages to be modified at each memory references. So LRU in its current format, it's not really efficient. So that's why people introduce several algorithms, that approximate the LRU. Okay. So hopefully this can actually make the algorithm more efficient. So one of the variations of the LRU page replacement algorithm is the aging page replacement algorithm. Now the aging page replacement algorithm is going to use two variables. One is the reference bit. The other one is aging registers. Okay, the reference bit is the bit associated with a page. So for each page, there's a reference bit, and it's set automatically by hardware whenever the page is referenced by any instruction. Okay, now the other one is the aging register. So it's also associated with a page, and the aging register may contain certain number of bits. Okay, depend on each of the algorithms. Sometimes we can set the aging register to 4 bits, 8 bits, 16 bits, or even more. So for each pages, let's say we have page 0, page 1, page 2, and the page 3. Now for this process, you have like 4 pages, page 0, 1, 2, 3. Now for each page, there's a reference bit, right? Okay, 1 bit. And then you have 4 pages, so they're going to be 4 R bit. And also for each page there's a aging register, I'm sorry. So then each has 4 bits in this case. And then you have, for each page there's a aging register. Okay. Now, if we use the LRU, so for the page references string, page reference string, right? So we may have 0, 1, 2, and then 0, 1, 2, 3, and 1, 2, 1, 2, 1, 3, for example. If that's the page references, okay? So then we know that for this time, page 0 is referenced, page 1 is referenced, page 2 is referenced, right? Now, using aging page replacement algorithm, we do not maintain pages sorted in the exact LRU order. So, but we group together pages referenced during the period of a D consecutive reference. Okay, so the value D could be 10, could be 20, could be 40. So the D is a parameter determined experimentally based on experience. Okay, for example, in this page reference, like a reference string, let's say we set D equals, let's say D equals 4. Okay, so every 4, consecutive references, we group every 4 consecutive references. Okay, so here's a page 0, page 1, page 2, page 3, right? So page 0 is referenced here. Page 0 is also referenced here. Now page 1 is referenced here. Page 2 is referenced here, right? Now page 3 is not referenced in this period, right? Now for the second period, page 0 is not referenced because it's not showing up over here, right? Now page 1 is referenced twice. Page 2 is also, page 1 is referenced, not page 0. So let me erase that first one. Let me erase this. Okay, so page 2 is referenced, and the page 3 is referenced, right? Okay, now what about this? 2, 1, 2, 1, 2, 1. So that means page 2 is referenced. Page 2 is referenced here, and page 1 is referenced here, and the page 0 and the page 3 is not referenced, right? So we divide this, using D into a period of consecutive references. Okay, now using the aging page replacement algorithm, we just check whether during that period of time a page is referenced or not. Okay, so let me change the color here. So in this case, page 0 is referenced, so the R bit will be 1 because page 0 referenced twice in the first period, right? Okay, so then page 1 is referenced, so the R bit will be 1. Page 2 is referenced, so the R bit is 1. Page 3 is not referenced in the first period, so it's 0. So in this period, the R bit is 1110. Now what about the second, this period? Okay, so in this period, let's see, let me actually erase the current value. Okay, so I erase this. So then page 0 is not referenced, right? Now page 1 is referenced twice, but it doesn't really matters how many times the page get referenced in this period. If as far as it's referenced, the value is 1. So page 2 is referenced, page 3 is referenced during that time period, right? And now for this period of consecutive references, then page 0 is not referenced, 0. Page 1 is referenced, page 2 is referenced, and page 3 is not referenced, so page 3 is 0 for this time period. Okay. So now, what does aging register plays a role in here? Okay. So now let's switch to the next couple of slides, so we will clearly see how this aging register can be used. Okay. Okay, now let's take a look at the example. Now in this example, we assume d equals 50. Now remember, in previous example, we assumed d equals 4. So what does that mean? So that means if there's a actually reference string, the page reference string, like a 0, 1, 2, 1, 2, 0, 1, 2, 3, 1, 3, 1, 3, all these page references, 1, 2, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. So if there's a long page reference string, right? So we're gonna group, 50 page reference together. Okay, and group another 50 page reference together. Group another 50 page reference together. Okay, so that means that d equals 50. Okay, now for the aging register, we use 4-bit aging register. Now let me explain what each of the bit basically means for the aging register. Okay, so now suppose the aging register contains 0, 1, 0, 0 for page, for example, page 2. Let's say page 2 has the aging register, right? 0, 1, 0, 0. Okay, so this first 0 indicates that the page 2 has not been accessed during the last 50 most recent references. Okay, because each bit basically represent whether the page is referenced in a 50 period of page references. Now, the most significant bit basically means the most recent, okay, the most recent references, 50 most recent references. 0 means that the page 2 has not been accessed during the last 50 most recent references. Okay, so that's most of 50 page references. Page 2 has not been accessed, so not referenced. Now, this the next one basically means, okay, this page 2 has been accessed at least once during the 50 previous references. Okay, so it's not referenced in the most recent 50, but in the previous 50 page references, it's referenced at least once. Okay, and then that's, so the reference even actually, another 50, page references before this 50. So this is the most recent one. That's the next most recent one, and that's the the oldest page references period. Okay, so that means now 00, that basically means if page 1, let's say page 1 is 0000, so that means in the most recent 50 page page references, page 1 is not referenced. Also, in the most recent 100, actually from 51 to 100 page references, it was not referenced. And it was not referenced here. It was not referenced here. So that means this page 1, okay, has not been accessed during the last 200, which is 4 times 50. Okay, you have total of 4 bits. Now each bit contains value 0, so that means in this 50 page reference is not referenced. In this 50 page reference is not referenced. So total of 200, okay, page references. This page 1 is not referenced. Okay, what does that mean? So that means page 1 has been in the computer memory but hasn't been referenced for the past 200 page references. Okay, now that's bad. That makes page 1 a potential candidate to be removed. Okay. Okay, so now let's study the example in much detail. Okay, so that's the initial state. Okay, so we have 4 pages, page 0, 1, 2, 3, and the referenced bit is all 0, and the aging register contains all 0. Okay, so pretty much these all pages has no history. Okay, so that's the initial state. Pages 0 to 3 are resident, and the R bits and the aging register all contains 0. That's good. Okay, after dereferences, so that means after 50 page references, okay, we just check whether during this 50 page references, page 0 has been referenced or not, has been accessed or not, right? So now after 50 references, the R bit shows that the pages 0 to 3 has been accessed at least once during the past dereferences. Now what does that mean? So page 0 to 3, pages 0 to 3 has been accessed. Okay, so that means pages 0 should be, the R bit should be changed to 1. Page 1, okay, 1 has not been accessed, during this 50 time period, right? So page 2, 3 has been accessed. So you got the R bit, change the R bit from all 0 to 1, 0, 1, 1. Okay, that's good. And then the next thing you need to do is you must be careful, because now before we actually try to record the next 50 time the period of page references, we need actually to shift, so all aging registers are shifted to the right. Okay, so that means this registered referenced bit will be shifted to here in the aging register. So it's a 1 0 1 1, right? So all aging registers are shifted to the right. So the R bit are shifted into the most significant positions of the aging register and then reset to 0. Okay, so this R bit were shifted to the most significant. Okay, and the other one is shifted. So that means this one shifted to here, this one shifted to here, and then this one shifted to here, this one shifted to here, this one shifted to here, and then this one shifted to here, this one shifted to here, shift here, shift here, and then the most significant bit will be replaced with the R bit. So that one, this column will be, shifted to the right, so it's actually out. So now we have this. So the R bit is reset to all 0, and the aging register becomes this. Okay. Now let's take a look at the next one. Okay, so now during the next D references, remember D is 50, right? So during the next 50 references, now pages 1 and 2 were accessed at least once. So the corresponding R bits changed to 0, 1, 1, 0 because page 1 and 2, page 1 and page 2 were accessed at least once. Okay, so then the next change is going to be the aging register are again shifted to the right. Remember the aging register is like this, right? So then the aging register is going to be first shifted to here. So this one is out. Okay. And this one shifted here. And this one shifted here. And then 1011, that's the previous page reference, then shifted here. Okay. So then we're going to actually also the R bits are shifted into the most significant one. So once you actually shifted this, you will get like a 1 0 1 1 0 0 0 0 0 0 0. So then the R bits, so the new R bits, which was this, right? Shifted here to the most significant here. So now the aging register becomes this. Okay. And then don't forget to reset the referenced bit, the R bit, to 0. Okay, so the R bits are shifted into the most significant register positions and then reset to 0. Okay, so here comes the exciting time. Okay, so during the next D references, D is 50 again. Now page 0 and page 3 are accessed. Okay, so in that case, so it looks like we gonna update the reference page 0 and page 3, right? Okay, and then we're gonna shift each of the bits in the aging register to the right. Okay, so we get rid of this one and then shift the R bit into the most significant one. So we actually get this. And then we reset the R bit to 0. Okay, so that's the status now. Now suppose page fault happens. Okay, because the next page wants to be loaded into the memory, but currently page 0, 1, 2, 3, these 3 pages occupy the whole physical memory. Okay, now we have to do the page replacement. Now with the aging page replacement algorithm, which page we should replace? Okay, or which page should be replaced? Okay, now It's very simple with the aging register. We just check the aging register. Treat this as a value. It's binary values. Now, what is this binary value? 1010. So that's binary number. So this is 2, this is 4, so it's actually 6, right? Now this is actually 4. Okay, now this is a 4 plus 2, so it's actually, oh, this is 1, 2, 4, 2, 4, 8. So that's 10. Okay, now this is a 4. Okay, and what is this? This is also 10. Okay, oh, sorry, this is 6. I say 6, but I still write 10. So now the aging register contains the value for each page. Now page 0 has 10, page 1 has 4, page 2 has 6, and page 1. Now the aging page replacement algorithm is going to select the page with the smallest value in the aging register. So you're going to replace the page 1 because page 1 has 4, which is smaller than the other one. Okay, so that's the aging page replacement algorithm. Now the only thing we need to figure out is if there are 2 pages with the same aging register, same smallest aging register, what we're going to do? Again, in this case, the arbitration rule going to apply. So you can randomly select one to be replaced. If there are 2, both has the smallest value, then we randomly select one. Now here's another page replacement algorithm. It's called the second chance page replacement algorithm. Now the second chance page replacement algorithm uses the R bit to divide all pages into 2 categories. One is recently referenced and the not recently referenced. Okay. Now if the R bit has a value 1, that means this page is recently referenced. If the R bit has a value 0, which means that's not recently referenced. So a page selected from the not recently referenced category. Now, the second chance page replacement algorithm is very similar to FIFO. However, the algorithm maintains a pointer that cycles through the pages when search for a page to be replaced. Okay. So again, it's like all the pages are actually located in the queue, and the pointer is just point to the next one, next to the next one. When the pointer reaches the end of the queue, it's going to go back to the top. So because of this circular nature, the algorithm is also known as a clock algorithm. Okay, so it looks like we have a page 1, page 2, or page 0, page 3, page 4, page 5, page 6. That's it's in a queue, and then after page 6 is back to page 0. So the pointer can actually just point to this one and then point to the next one, point to the next one. So it's just going in circle. At a page fault, the algorithm repeats the following step until the page is selected for replacement. Now, if the pointer is at the page P with R equals 0, so that means the R bit is 0, then we select the P and advance the pointer to the next page. So we replace that page and then advance the pointer to the next page. Now, otherwise, if the R is 1, so the reset bit is 1, so that means the page was recently referenced. So we reset R to 0. Okay. Don't replace the page, and then advance the pointer to the next page and continue the search. So that means if the pointer to the page pointer to a particular page. Now the reference for the page is 1, so that means the page was recently referenced. Then don't replace the page. okay, then you point to the next page. But you reset the R bit to 0. So that means I give you a chance because you were recently referenced, so I don't replace you. But I'm going to reset the R to 0. So next time when I actually reach you, if your reference bit is still 0, you will be replaced. Okay, so that's the reason why it's called a second chance page replacement algorithm. Okay, so let's take a look at an example for the second chance page replacement algorithm. Now, in this example, we have 4 friends. Okay, friend 0, 1, 2, and 3. And also we have 4 pages, page 0 through actually page 3. Now, all the pages from 0 to 3 are resident in the friends number 0 through 3. Okay, so each page is actually resident in the friends. Now, the pointer for starting a new search is at page 0. Okay, here's the pointer. Okay. Now, also, for the second column, basically it shows the value for the R bit, the referenced bit. So page 0 has reference bit 0, page 1 has reference bit 1, so that means page 1 was recently referenced. Page 2 has reference bit 1, 0, page 3 has reference bit 0, right? Okay, so now let's start. Okay, so the next page reference is page 2. Okay, the page 2 will be, referenced. So the page replacement algorithm is going to check whether page 2 is in the physical memory. So it checks the physical memory and find out page 2 is actually in friend number 2, right? So that means there's no page fault. Okay, so then all the page is going to be staying. However, this page reference may actually change the R bit, right? So let's see. So 2 is referenced here. So that means the value 2 is going to be 1. 1 is still stays 1, 0 is 0, and 3 is 0. Okay, so the pointer still pointing to 0. There's no change. Now the only change is this. Okay, the reference bit for page 2 actually changes from 0 to 1. That's good. Okay, so now we have our next page reference, okay, which is 1. Now the operating system is going to check the page replacement algorithm, going to check whether 1 is in the physical memory. And we check out, so 1 is in frame number 1, right? So there's no page fault. So all the pages still stays where they are. And this reference may change the R bit. Let's see whether you're going to change the R bit. So it's reference 1. So this is going to change the R bit. Actually, the R bit for page 1 is already 1. So, this reference never going to change the value. It still stays 1. So it's referenced. So the rest of the reference number still stays the same. Okay. And the pointer still stays in page 0 because there's no page fault. Okay, so now let's take a look at the page reference, which is 4. And the algorithm check the computer memory to see whether 4 is in the memory. And then we find out page 0, 1, 2, and 3, they are all in the memory, but not 4. So then page fault happens, right? When page fault happens, now we're going to replace the page. Now, which page is going to be replaced? the operating system, the second chance page replacement, are going to check the pointer, so which is currently pointing to page 0. So page 0 should be replaced, unless the reference bit for page 0 is 1. Then the page replacement algorithm is going to give the page 0 a second chance. But in this case, the reference bit is 0. So then page 0 is going to be replaced. Okay? It will be replaced. Okay, so 0 is going to be replaced with 4. So then the reference bit for 4 should be 1 because it's referenced once. Once it's loaded into the memory, and then it counts as one reference. Okay, so then page 1 still stays in the same frame. Page 2, 3, they don't change. And also, the reference value stays the same. Okay. Now, the pointer is going to actually jump to the next page in the queue, right? Now, here comes the next page reference 0. And page 0, again, page 0 is not in the physical memory, right? Because we have page 4, 1, 2, and 3. Okay, not 0. So page fault happens. Okay, now in this case, the pointer is pointing to 1, the page 1. Then the next thing, what we're going to do for the next time? For the next thing, what's the next thing we're going to do? We're going to check the reference bit, right? If the reference bit is 1, we're going to give page 1 a second chance. So then we find out the reference bit is 1. That's good. So page 1 going to stay. However, the reference bit for page 1 going to be changed to 0. Okay. Now what's next? So then we're going to move the pointer down to 2. Okay, so that was the point. But now we move to 2. And then 2 should be replaced if the reference bit for 2 is 0. Now it is 1, right? So that means 2 going to stay. Okay. And the reference bit will be changed to 0. Okay. So then we're going to move the pointer down to 3. Now that was the previous point. Okay. So 3 should be replaced unless the reference bit is 0 or 1. Unfortunately, it is 0, right? So 3 should be replaced. Okay. So we're going to replace 3 with 0. And since 0 was added and just referenced, so the reference bit for 0 is going to be 1. Okay. So the reference bit for 4 stays as 1. And then once 3 is replaced by page 0, so the pointer going to actually, because it's already at the bottom of the queue, so the pointer going to switch to the top, right? So that's the next point. So this is actually the second chance page replacement algorithm. So it's also pretty simple, but we need to keep an R bit and give all the pages with R bit value 1 a second chance. Thank you.